And there's a special case. A special case would be, what if psi, the state psi, was actually one of the eigenvectors of the A operator, right? So let's say psi is equal to phi A, one of the eigenvectors of A. Well, then what we can do is we can plug it in, all right? So we'll forget about the time for now, right? So we're going to have phi A, phi A. We look at our solved eigenvalue problem. We see the A operating on phi A. We can replace that with the eigenvalue multiplied by the eigenvector. And we have phi A, the number, phi A. This is a number, so it can pop out, right? And then we have A, phi A, phi A. And then we notice, oh, this is a scalar product. What do we know about scalar products of a vector with itself? Assuming we did our work correctly at the beginning, these vectors should all be normalized, meaning that this scalar product, just like the one for the state vector itself, this has to equal 1. Then we get out A. So all that's saying is if the state of a system is one of the eigenvectors of the A operator, it essentially flies through the Aometer unscathed. And that's, in some sense, you can think of that as like a working definition of what it means to be an eigenvector of an operator. Even though the operator might be doing some horrible things, taking derivatives, multiplying by who knows what, you know, dividing by r. Nevertheless, your function sails through, and all it does is it gets scaled by a value, the eigenvalue itself. All right, so that's what the eigenvectors are all about. Expectation values are there. And one thing that we're going to do next is ask this question. Let's take a little bit more look at this set of eigenvectors. So remember, we have this A operator. It has all the eigenvectors available to it. They are orthonormal if it's a Hermitian operator, and all of the eigenvalues are distinct, for example. Then that's easier. If they're degenerate, it's not impossible, it's just a little bit more tedious. Then what that means is that I have a complete set of states. I have a complete basis, just like here. Right? As long as I'm in 2 dimensions, these two vectors, like I hat and j hat, can be used to describe any vector in this space. Okay? Well, that's true also for the Hilbert space spanned by the eigenvectors of the operator that you solved the eigenvalue problem for. Right, so why is that interesting? That's interesting because what it means is, if I imagine this operator that I make by putting an eigenvector in the ket form and multiply it by the eigenvector in the bra form right next to it, well, this is an operator, right? Because when I multiply or operate with this on a vector, I'm going to get back, let's call this just v for whatever vector I want. What do I get? Well, this here is a scalar product, so this is going to be a number. And this is a vector here. Right? So anytime you operate with something on a vector and you get back a vector, that means it was an operator. Right? So this thing here is an operator. Now, does it have an interesting property? It does. Let's take a look at what that is. Let's look at doing it twice. Phi A, do it again. Phi A, phi, oops, I did it wrong. Phi A. What do we see here? Oh, look in the middle. This is 1, because we have normalized vectors, of course, and we get back what we had before. Right? Well, when an operator squared is equal to an operator itself, the term for that is idempotent. And it means that it's a projection operator. Right? It is an operator which acts a little bit like a filter. If I send a vector through it, I'm going to get a new vector out, but it's going to be the one that points in the same direction as the vector of my filter. You know when you've used this, if you're an optical person, is when you have a polarizer. A polarizer does this. It takes a vector of light that could be pointing in any direction, but based on the polarization of the light that you have. And what comes out is light that's polarized in the direction, parallel to some axis of the polarizer. your sunglasses that are polarized do this. Because the light bouncing off a flat surface tends to be horizontally polarized, you put in a polarizer in your glasses that's vertical, it'll cut out primarily the light that's reflected off the ground, and that gets rid of the glare. It's particularly useful if you're fishing, if you want to get rid of the glare from the water and just see the fish, or even if you're not fishing but just want to see the fish, this is very helpful. Of course, if you're driving or riding a bike or whatever, it's also can be convenient to have polarization. Of course, it makes looking at your phone or your watch a little problematic because those are also tend to be polarized. Okay, so a polarizer is a kind of projection operator. It takes an arbitrary vector input and it gives you out one vector that's aligned along it. Now we're going to use this quite a bit because what do we need to do? All right, so one of the things that you'll learn about this board, which I like, is it turns out to be very hard to erase. All right. So the last bit that we're going to do with this issue of the projection is we're going to look at what happens if you project an arbitrary vector onto all of the eigenvector projections that there are for a particular operator. Remember, we got these phi a's. They're the solution to some sort of eigenvalue problem. It could be this Schrödinger equation. That's for the Hamiltonian, but there's certainly other operators you could imagine. But let's imagine we have an input vector, okay? And we operate on it on all of them. How am I going to do that? I'm going to write phi 1 plus phi 2, oops, and so on. Now, there might be an infinite number or it might be a finite number of them. Okay? Well, if I operate, I'm going to get the component, or not the component actually, the magnitude and the vector corresponding to every single one of these projections, right? And as long as this set of vectors spans the entire space that this vector lives in, then if I look at the projections of all of these on this vector, sorry, on all of these eigenvectors, I have to recover my vector. Right? I have to get this back. It's just like this. If I take this vector, b, and I decompose it into, so let's write it out, the vx component times I hat plus the vy component times j hat. And remember what vx is, right? Vx is the x component, and that's the scalar product of the v with the I hat operator. The Vy is the scalar product of V with the J hat operator. Right? And so you see that there's a kind of similarity because this I can plug the x back in. I can write V dot I hat times I hat plus V dot J hat times J hat. This is the magnitude, this is the vector. This is the magnitude, and this is the vector. Right? So you could have used the projection representation just as easily. Right? So what that means is if this is the same, if this side and this side are the same, that means that this whole thing is equal to 1. So far you've seen about 3 of the questions that were on the pre-term quiz have been discussed so far. So you write this out more compactly in this form. Which is to say, if I add up all the projection operators onto each of the eigenvectors of the operator A, it's equal to the identity operator, but we often just write a 1. Okay? Sometimes this is called, very big words, the spectral resolution of the identity. It's saying it's taking the identity operator 1 and resolving it, separating it into each of the different contributions from each of the different eigenvectors. And it's very common, mostly in the sort of physics textbooks, to talk about the spectrum of an operator, even if it's not literally like something that you would go in the lab and measure a spectrum of. It just means it's the set of eigenvalues that match or connect to each eigenvector. Okay, so the spectral resolution of the identity, super important. Half of our derivations will involve nothing other than putting this in very clever places in our equations. But more importantly, what it allows you to do is to switch from one basis to another one. Because if I have some vector like v, and I want to switch it to be in the representation of, or in the basis of x and y, I simply figure out what's the sort of Rosetta Stone for translating from v into x and y. Right? That's what we're going to do a lot of the times, and that's what you do almost all the time in quantum mechanics. You start out with a basis, then you figure out how do you have to transform that basis to get, for example, eigenvectors of another problem that you're interested in. If one basis came from the eigenvectors of a reference Hamiltonian, like the one we talked about last time, but you're not interested in this, you're interested in the Hamiltonian h naught plus h primed, whatever that happens to be, well then you just need to figure out how to rotate these vectors to become the eigenvectors of the new Hamiltonian. Okay? All right, so that's the sort of the layout for the first bit of the structure of operators, expectation values, projection operators, resolution of the identity, reminder of the Born interpretation. Yeah, and we'll keep going from there.